Welcome back to linear algebra. In this video, we're going to talk about matrix transformations. A matrix transformation is a special type of function whose domain and range, input and output values, are vectors. You should be familiar with the basic ideas of functions already at this point in your academic career, but before we get into talking about transformations and some of the specific properties, I want to take a minute, go back, and review some of these ideas, these basic ideas on functions, just to make sure that we're all on the same page with notation. So let me get my head out of the way and let's dive right in. Right? And right away, this notation, depending on your experience with calculus, you may or may not have seen it before. We read this: a function f maps from D to R. And then when we get to the vocabulary, a little bit more that may or may not be familiar. All right, so a function f is a rule which assigns each value in set D, which we call the domain of f, to exactly one value in set R, which we call the codomain of f. And where I wrote codomain here, again, depending on your background, you may have seen this before, you may not have, but you may have been expecting me to say the word range there instead. And for reasons that we'll be getting into throughout this lesson and the next couple of lessons, it's useful to have an intermediate step before we get to the range. Right. To get there, let's look at another set. I'm going to call this set S. It's a subset of the domain. So the image of the set S under the function f is denoted and defined f of S, and it's the set of all values f of x so that x is in S. And the first thing I want you to notice about this definition is that the image of any set will be a subset of the codomain, right? That's the definition of the function. X has to be a value in the domain, and then f of x has to be a value in the codomain. So if we collect a set of values f of x, we are collecting a set of values that are from the codomain. F of s is definitely a subset of the range. I'm sorry, I'm getting ahead of myself. F of s is definitely a subset of the codomain. The next thing I want to talk about is the range. And the range of f is f of d, the image of the entire domain. And now that we have that definition, I can talk a little bit about why we care. There are two important aspects of functions. The first one is something that you didn't really spend too much time with in your basic algebra and even calculus courses. In algebra and in the first two semesters of calculus, you deal almost exclusively with real-valued functions of one real variable. It is very easy to say that the things you put into the function are real numbers and the things you get out of the function are real numbers. In this course and in several other courses at the same level, multivariate calculus, discrete mathematics, we start looking at functions a little bit more generally. And at that point, it becomes important to notice what kinds of objects are you putting into the function and what kinds of objects are you getting out of the function. So are we taking a function that takes on real numbers, two-dimensional vectors, three-dimensional vectors, something else? And are we getting out two-dimensional vectors, three-dimensional vectors, real numbers, complex numbers, something else? That's what the domain and the codomain are there to talk about. The further question of which things do we actually get out from this is where the range comes into play. All right, so a simple example to see what I mean. The squaring function, f mapping from the real numbers to the real numbers, given by f of x equals x squared. We are, I hope at this point you are very familiar with the squaring function. It tends to be the classic example. That's not an arrow. It tends to be the classic example we use in algebra and even calculus because it is interesting without being complicated. All right, so the squaring function has a graph that looks something like that. The domain of the squaring function is all real numbers. We can put a real number into the function. The codomain is also the real numbers. When we put something into the function, we get out a real number. We can be more specific than that. Right? The codomain is all real numbers. That's the kind of object we get, real numbers. The range is just the numbers from 0 to infinity. Right? The squaring function, when you put a real number into it, will spit out a positive number, never a negative number. And so that is an interesting additional property of the function. But again, as we're continuing onward, we're going to be looking at some functions that spit out different kinds of vectors. Even if I tell you that the function we are looking at is a vector function, it inputs a vector, it outputs a vector, that still leaves a pretty big question mark because we have two-dimensional vectors and three-dimensional vectors and five-dimensional vectors and 27-dimensional vectors. And so we want to be able to be specific about those sorts of things as we talk about our functions. All right. A transformation, which we'll denote using capital T, mapping from Rn to Rm, is a function whose domain and codomain are each vector spaces. An operator is a transformation whose domain and codomain are the same vector space. Right? So when we say transformation, we mean a specific type of function that acts on vectors. When we say operator, we mean a specific type of transformation which acts on a single type of vector. Spoilers for things to come. We're going to be looking at ways to generalize our idea of vector beyond the Euclidean vectors in the second half of this course. And so this terminology is going to become a lot more general than it seems right now. If you've come across the idea of a transformation or an operator in a different course, you may have seen them used in very different contexts than things working on Euclidean vectors, and that's because there are other things that are still vectors. Right? But every operator is a transformation. Every transformation is a function. We have this language that's going to be a little bit more specialized. I'm not going to use operator all that much. I'm generally going to be talking about transformations. Even when it is from a vector space to itself, I'm going to deal with calling everything a transformation and talking in general terms as much as I can. All right. So here is a relatively straightforward transformation. Maps from the three-dimensional vectors to the three-dimensional vectors, so it is an operator. And I'll define it by the transformation on x, y, z gives you the vector x squared y squared z, z squared x. Then if I want to evaluate the transformation on, say, 2, 3, 5, I can calculate that. X is 2 squared times y, which is 3. Then we'll have 3 squared times 5, and 5 squared times 2. Right? 2 squared is 4, 4 times 3 is 12. 3 squared is 9, 9 times 5 is 45. 5 squared is 25, 25 times 2 is 50. So a transformation is just a function. We can define transformations using the same kinds of language we've used for defining functions since you were in high school algebra. That's not really the interesting thing. The interesting thing is looking at ways of defining transformations that we couldn't quite use when it was real valued functions. A matrix transformation is a transformation T defined by matrix multiplication. That is to say, T acting on some vector V is going to be defined as A times V for some M by N matrix A. All right. For example, consider a transformation T going from R3 to R3. given by t acting on some vector v is equal to the matrix 1, 1, 1, 0, 1, 1, 0, 0, 1 times v. Then we can evaluate this transformation. Let's use the same vector we used before, 2, 3, 5. Well, that means we're going to take 1, 1, 1, 0, 1, 1, 0, 0, 1, and we're going to multiply it times 2, 3, 5, and row and column. 1 times 2, 1 times 3, 1 times 5, 2 plus 3 plus 5 is 10. Second row with the column. 0, 3, and 5 is 8. Third row with that column, 0, 0, and 5 is 5. Right? So we can evaluate these transformations given by matrix multiplication like this. It's a nice, convenient way of defining a transformation relatively compactly. We call a transformation linear if and only if it preserves linear combinations, which is a bit of an odd statement, but we've been talking about linear combinations quite a bit in this course, so hopefully it's starting to make sense. Right? A linear combination of two vectors v1 and v2 is some constant c1 times v1 plus some other constant c2 times v2. And when we say that it preserves linear combinations, what we mean is that the transformation acting on this linear combination is the same linear combination of the same transform acting on the same two original vectors. And this finally gets us to what we're really going to be looking at in this course. All right, we are how far into the course, and I can finally define what linear algebra is. Linear algebra is the study of linear transformations and how to turn things into linear transformations, how to recognize that things are linear transformations, how to use the fact that something is a linear transformation in order to make your life easier. But it all comes down to linear algebra is the study of linear transformations. I called this video matrix transformations, so it should make sense that the matrices that we've been dealing with are in fact linear transformations, and that's the next place I want to go. I claim that every matrix transformation is a linear transformation. All right. Proving this isn't too bad. In order to do that, the first thing we need is a matrix transformation. So let's define a matrix transformation T. Then we need to have that transformation act on a linear combination, C1 V1 plus C2 V2. And of course, the definition of the transformation says that this is just A times C1 V1 plus C2 V2. And a matrix transformation or matrix multiplication like this has its distributive property and has its associative property. So we can distribute A times C1 V1 plus A times C2 V2. And we can use the fact that matrix multiplication and scalar multiplication associate to get the C1 out front and have A times V1, and likewise get the C2 out front and have A times V2. One last step, A times V1 is exactly the definition of my transformation acting on V1. And A times V2 is exactly the definition of my transformation acting on V2. And so we have exactly what we needed, right? That is exactly the condition of this transformation being linear. All right. That's an interesting and a powerful result. The surprising thing is that's actually the weakest result that we're going to be looking at in this video. Because if we take the relationship the other way, it turns out that that is also true. And this is the part that becomes mind-blowing. Every linear transformation can be written as a matrix transformation. All right, in order to prove this, we're talking about linear transformations. So I guess the first thing we need is to establish a linear transformation. And if every linear transformation can be written as a matrix transformation, it turns out that the easiest way to deal with this is to establish a particular vector. I'm going to call it U. I could also call it V. It doesn't really matter. But I know that a vector in Rn is a column vector with components u1, u2, down through to un, where each of those components is itself a real number. And the reason that I want to name specifically my vector by its components is to remember that this is not the only notation we have for a vector in Rn. We also have the unit vector notation. I can take the first component and multiply by the first basis unit vector, E1. Remember, that's the vector with a 1 in the first component and zeros everywhere else. I can take my second component of U, U2, and multiply it by E2 hat. That has a 1 in the second component and zeros everywhere else. And I can keep doing this for all of the components up until UN, EN hat at the end. Now I have my linear transformation, I have my vector, I can evaluate the linear transformation at that vector, and I can take advantage of the fact that we assumed that this transformation was linear. A linear transformation preserves linear combinations. And the way I've written vector u is as a linear combination of the basis unit vectors. So I get u1 times L on e1 hat. I get u2 times L on e2 hat, all the way down to un times L acting on en hat. All right, I'm going to break into the middle of this proof, which is terrible mathematics notation. But this equation right here is a powerful result in and of itself. The only thing we need to know about a linear transformation is what happens to the basis vectors. What happens to E1 and E2 and all the way down through to En. If we know what happens to each of those things, the transformation on any other vector is just a linear combination of those. That's actually going to be the most important result out of all of this, followed very closely by, to create a matrix, I'm just going to create a matrix where the columns of matrix A are these outputs. L acting on E1. Remember that L maps from Rn to Rm. So the output of L on E1 is a vector in Rm, an m-dimensional vector. Likewise, L acting on E2 is an m-dimensional vector. So this construction gives me an m by n matrix. The columns are the results of my linear operator acting on each of the basis vectors, each of the standard unit vectors. It has n columns because there are n basis vectors in Rn. It has m rows because the linear operator spits out vectors in Rm. We know the codomain, and this is why knowing the codomain is useful. It's also useful to remember that when you multiply a matrix times a vector, what you get is a linear combination of the columns of the matrix. You're going to get the first component of U1, times the first column of A, L acting on E1. You're going to get the second component of U times the second column of A, L acting on E2. And I'm running out of screen space, but that continues through the rest of this. And that is, in fact, exactly what we got when we defined our L of U in the first place. I love this proof because it gives us more than we think it's going to at first glance. Not only do we have the fact that every linear transformation is a matrix transformation, we also have everything we need in order to write that matrix. And this is usually how linear transformations are going to go in this course. We're going to have a transformation we want to work with. We're going to learn what it does to the standard basis vectors, and we're going to use that to write the matrix and use the matrix to calculate the value at other places. That is the entire process and procedure. All right. So as an example, I might want to write a linear transformation to represent rotating a vector in the xy plane counterclockwise by 30 degrees. This is surprisingly a very important application of linear algebra and matrix transformations. We can use matrix transformations to represent rotating things, and this is how computer graphics work. Computer graphics are all based around working with matrices. All right. So let's take a look at the XY plane, and let's take a look at our standard basis vectors, E1 hat, E2 hat. I don't want to have to deal with rotating every vector individually. I want to find a nice simple representation of it. And we just saw that if I can just figure out what happens, let's draw that in a different color. If I can just figure out what's going to happen to my basis vectors, when I rotate by 30 degrees, that's going to give me everything I need to know. Well, the nice thing about the standard normal or the standard unit vectors is that they have a length of 1. So we know what the length is. We know what the angle is. We can draw over and form a couple of right triangles and use that. So E1 is going to go to this guy. It's actually an angle in standard position, which makes the situation really nice. You're going to have cosine of 30 degrees, and you're going to have sine of 30 degrees. Right? Go through and remind yourself of the trigonometry if it's been a while since you've done trig. But that's a standard result out of trigonometry. And if you know your trig functions at special angles very well, then you can actually get the cosine of 30 degrees is the square root of 3 over 2. And the sine of 30 degrees, whoops, get my head out of the way. Sine of 30 degrees is 1/2. We can do the same thing with E2. Right? It's a little bit trickier because the angle is not in standard position. But if you pay attention and think about how these coordinates are going to fall in, the x component is the opposite side of the triangle, and it's going in the negative direction. So negative of sine of 30 degrees. The y direction is the adjacent side to that angle. So cosine of 30 degrees there. So knowing our special angles, -1/2 square root of 3 over 2. And then from there, we can write our transformation matrix. Let's call it R for rotation matrix. The first column is going to be the result from rotating E1, root 3 over 2, 1/2. The second column is going to be the result from rotating E2, -1/2, root 3 over 2. If you care to, you might see these results. Somebody might factor out the 1/2 just to make it look a little bit nicer. Square root of 3, -1, +1, square root of 3. Either version is perfectly acceptable. There's no reason that one or the other is better. They both absolutely work. Right. So if I had a vector going off in some other direction, right? If I wanted to rotate vector v with components, let's say 5, -7, counterclockwise by 30 degrees. Well, I can just apply my linear transformation R to that vector, which means multiply my matrix, root 3 over 2, -1/2, +1/2, root 3 over 2, times the vector in question, 5, 7. I should have used even numbers so the fractions would cancel out, but I did not. And let's see, first row times this column, root 3 over 2 times 5, -1/2 times 7. We get all told that's going to be 5 root 3 minus 7 all over 2. And then second row with column, 1/2 times 5, root 3 over 2 times 7, 5 plus 7 root 3 over 2. If you want to check and see that that works, I invite you to grab out a ruler and protractor, draw this vector very carefully, rotate it very carefully, and see that these numbers work out or close enough to them if you grab out pencil and paper or a calculator to do the computation. But instead, let's move onward. Linear transformations in 2 dimensions and sometimes in 3 dimensions are fairly straightforward. We can draw the pictures. When we get to higher dimensions, it's a little bit more challenging. And so most of the time, these transformations are going to be defined explicitly. So for example, L acting on E1 might be 2, 1, 0, 0. L acting on E2 might be 3, 2, 1, 0. And L acting on E3 maybe will give us 4, 3, 2, 1. All right, I said that this transformation went from R3 to R4. There are 3 standard unit basis vectors in R3. I have the transformation defined on each of them. There are 4-dimensional vectors coming out, R4. Everything works out nicely. All right. And I'd like you to take a couple of minutes and work through this. Write a matrix which represents this linear transformation, and then use that matrix to evaluate the transformation on the point 2, -1, 3. All right. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.